couple days, we've been talking about the circular motion, talking about the centripetal force that needs to be acting on an object moving in a circular path. Today, like I mentioned before, we're going to talk about a vertical circle, so things going up and down as they're traveling in a circular path. To get us started with that, I wanted to watch a short little video that is from a short series called ESPN Sports Science. So, this one is about G-forces and how it relates to a fighter jet versus a race car. Okay? So, it's about 3.5 minutes long, so let's get this started, and then we'll discuss.
Indy race car drivers and fighter jet pilots both endure extreme G-forces. But how do the G-forces in a fighter jet compare to an Indy car? To find out, I get suited up for science.
So we got a vest here, John, that has accelerometers that's going to measure G-forces in all 3 axes. Just don't throw up on my stuff.
I'll be riding along with pilot Dave Riggs in his Aero L-39C Albatross jet. And when the jet takes off, it rapidly accelerates to a speed of 500 miles an hour.
We did a lot of high G maneuvers. All of these maneuvers put a lot of stress on the body.
It's like being in a washing machine. 4 Gs. 6 Gs. 7.3 Gs. Our data reveals that at peak moments, in bursts lasting less than 0.2 of a second, we're pulling 7.3 Gs. This makes my 160-pound body feel like it weighs over 1,100 pounds.
I can't even lift my arms. My face is just shuddering. I've never felt my body that heavy before.
To compare the G-forces of the jet to an Indy car, even listed driver Ryan Hunter-Reay. Wired up with the same sensors I wore, Ryan puts the pedal down on the brickyard. At peaks of 230 miles an hour, this 700 horsepower Indy car subjects Ryan to over 4 Gs in a single turn, lasting an average of 6.6 seconds. That's 33 times longer than the duration of the maximum Gs I experienced during this maneuver. I can tell you that 3 to 4 Gs is no joke, and he has to do it 800 times in the race.
You can't breathe normally. You can't just intake that oxygen when you want it. It has to be straight away.
In the 3.5-hour Indy 500, there are over 88 minutes of turns. And in those turns, Ryan experiences 3,200 cumulative Gs. That means the forces his body sustains will total more than 500,000 pounds. When it comes to G-forces in the Indy 500, it's not only about how many Gs, it's about how long those Gs last. For Sports Science on ESPN, I'm John Brakes.
We should watch The Simpsons next. Just saying.
All right, so let's talk about what we were just looking at there. The problem set that I gave you yesterday that we didn't end up doing is called calculating centripetal force vertical circular path. So to demonstrate, to start off, right, we're going to start with this. Okay? A demonstration that we did earlier, okay, but just to review, right, is this object accelerating?
Yeah.
Yes, right? We keep changing directions. And that means if it is accelerating, it's got to experience what? Net force. And we call that net force what? Centripetal force, because it always points towards the middle. But like we discussed, centripetal force has to come from somewhere. What's providing centripetal force in this situation? Well, me, I'm not touching the ball, right? So the strength, right? Except when we go in this path, we have something that we have to take into account that we haven't before, and that's gravity. All right? When this ball is up at the top of its motion, up here, which way is gravity pulling on it? Down. But when it's down here, which way is gravity pulling on it? Still down. Okay, that doesn't change. But because the path this object is taking is going up, down, when it's up here at the top of the motion, gravity is acting downward, but in relation to the circle, which way is it pointing? It's pointing towards the middle. And that makes it part of centripetal force, right? It's helping centripetal force at that point. But at the bottom, which way is it pointing? Down, but in relation to the circle, which way is it pointing? It's pointing away from the middle, right? So is gravity helping or hurting us in that spot? Gravity's hurting in that spot, right? It's not contributing to the centripetal force. So the string has to do more stuff, right? Does that make sense? Okay. So let's take a look at that to start off, and then we'll talk about the G-force thing. Okay. All right. So let's take a look here at number 1, and specifically number 1A. So it says, a ball attached to a string is rotated at a constant rate in a vertical circle with a radius of 85 centimeters. Ball has a mass of 0.3 kilograms. It rotates with a tangential speed of 4.15 meters per second. So A says, what is the force supplied by the string at the top of the motion? What do we call a force applied by a string? Tension, right? So in this problem, problem A, we are trying to find tension. Okay, what is the force supplied by the string? Things they gave us to work with, right? They told us that that ball has a mass of 0.300 kilograms. It told us that the object is moving in a circle with a radius of 85 centimeters. We don't want it in centimeters though, right? We'll call it 80.850 meters. And then, right, tangential speed of 4.15. Okay, good there? Questions? Okay, let's draw our picture. Here's the circular path of the object. And this question specifically is asking us about an object up at the top of its motion. So, as we just discussed, here's the center of rotation. We know that there's at least one force that is acting on that ball up at the top. And what is that force? Gravity. Regardless of whether it's going in a circle or not, gravity is going to be acting on it. We can't get rid of that. So we know that there is a gravitational force there. Do we know how much that gravitational force is? We can figure it out, right? So, you plug that into your calculator and you find out the gravitational force acting on that object is equal to what? 2.94. Now, is that gravitational force enough to move this object in a circular path? At this point, do we know? No. Because this is pointing towards the middle, right? Meaning that that's going to contribute to what? Right? It's also centripetal force. Do we know how much centripetal force is required for this object to move in a circular path? We don't yet, but what does the amount of centripetal force depend on? It doesn't depend on gravity. It depends on mass and speed and radius, right? Can we figure out what the centripetal force is for that object? Yeah. M, 0.3, V squared, 4.15, over R, 0.85. Run that through your calculator and find out how much centripetal force that this object requires in order for it to go in a circular path. much centripetal force is required for that ball to go that fast around that turn. Is gravity going to get the job done for us here? No, because we need this much centripetal force, and right now we only have that much force coming from gravity. So, is gravity the only force that's acting on that object up at the top? Can't be, right? We said it's also attached to what? A string, right? And that string, because that's what strings do, they pull, right? It just so happens that up at the top of the motion, that string is pulling towards the center, okay? And that means it's centripetal force, or it's helping centripetal force. So we said all of our problems in this unit start with f of c equals something. What is f of c equal in this problem? F of g plus f of t. Now, based on the calculations that we've already done, can we figure out what f of t is going to be? Shouldn't be real hard, right? You should. Oh, you have a question?
Hi.
Go.
Oh, this is funny. Did you do that on purpose?
No.
It's like, I'm going to save this problem.
Quite honestly,
Thursday.
I've never done this problem on Pi Day before. You guys are actually ahead of where we usually are this time of year.
Well, we started
So-
2 weeks early, so.
Well, that's true. So maybe that's why you guys are so far. All right, Roberto brings up a good point. Okay, this is an extreme case because which way is gravity pointing at the very, very top? In, but all of gravity is pointing in, right? At other places in this circle, like this, right, gravity still points downward, but now our frame of reference sort of changes here. We're not really worried about up or down. We're worried about the circle and whether it points into the circle or whether it points away from the circle. So, in that case, right, oh, look, good old components, right, except that component's pretty crappy. So, let's put it like that, right? So, some of it is helping, but some of it isn't, okay? So, that's why we can really deal with it more here, all right? And then obviously what would be the other place where we're going to deal with it? At the bottom, and that's what part B is like, okay? So yeah, does gravity help along the way? Yes, but at the very, very top, all of gravity is pointing directly straight down, which just so happens to be right towards the center. Does that make
Do
sense?
we have to worry about anything besides the top?
No, I won't make you do any other parts. So it gets a little complex mathematically, you know, but at this point I won't make you do anything except top or bottom. Okay. So, speaking of, let's go bottom. For part B, so same question, right? Same information, but now support force supplied by the string at the bottom. We're still looking for tension. Going back to our picture, right? There's the circular path. There's the object. Is gravity still acting on it? Yeah. How much is gravity still acting on it? This isn't going to change, right? Here, let me just do this. I'm going to copy this. Paste it on, right? But now, the problem being, in relation to the circle, right? Which way is it pointing? Is it pointing towards the middle? No. So is it helping centripetal force? No. We know that there has to be a force that points towards the middle to make that happen. Where is that force coming from in this problem? The string, right? So here is our tension force, okay? But that tension force is going to have to be bigger than it was before. Why? Because this problem starts like this. F of c equals something. What is f of c equal to in this problem? F of t, right? But can we just disregard gravity? You can't, right? So it's still plus f of g. Okay?
Wait, wouldn't it be minus over G?
Technically, we talked about centripetal force is actually a net force, right? Because it causes what? It causes acceleration. So how do we calculate net force? Net force means what? It means sum, right? The total of the forces. But if we adjust our frame of reference here, like I said, we're not really worried about up or down. We're really worried about into the circle or out of the circle, right? So that being the case, how much centripetal force does there have to be for this ball to go in this circle at this speed? This is still 6.08. That doesn't change, because that depends on the ball itself, the speed of that ball, and the circle that it's going around. Do we know what the tension force is yet? We don't. But we do know that there is a gravitational force, but which way does that gravitational force point in relation to the circle? Well, it points down, but in the circle, it points out of the circle, right? So what are we going to do with that? Okay. It's not helping our case here, right? So we're going to make that negative. Do we subtract it? Yeah. In the end, you end up subtracting it. But to be consistent with the notation of net force, we have to go this way. Okay? That being the case, you solve this, and I think you get 9.08 or something like that. 9.02. I probably could have done that in my head, but... Alright. How's that? Okay. Conceptually, I won't start a new problem. I just want to talk about it conceptually. If we take a look at number 4. So number 4 says, 80 kilogram stunt pilot has been diving vertically with a speed of 75 meters per second. He has to pull out of the dive while maintaining his speed, but centripetal force must not exceed 7 Gs. And we'll talk about what that means tomorrow. Here, in order to make this plane go in a circle, it has to have a centripetal force. Where does the plane get its centripetal force from? Because in this case, which way is gravity pulling on it? Down. The plane gets its centripetal force from the air. You change the flaps on the plane, and that changes which way air pushes on the plane. Where does the pilot get his centripetal force from? The plane, because the plane pushes on him. Very similar to how you're all just sitting here right now. Is your seat pushing on you? Yes, it is. How much is your seat pushing on you? Just as much as gravity pulls on you. Okay? Yes. That being the case, right, what do you do? What does your seat do to you if the two forces are the same? Doesn't do anything. It's equilibrium. But if your seat starts pushing on you harder than gravity's pulling you down, what's going to start happening? You could start flying, or you could start accelerating somehow, some way, and that's what we'll talk about tomorrow. Okay? So tomorrow we'll deal with G-forces and what that means.